Let everybody grab a seat. Sorry that the conditions are a little bit crowded here. As everybody knows, the conference room is finally, after a decade of asking, being redone. So, you know, hopefully we'll have a conference room in a few weeks that's, you know, maybe a little better than this. But for the time being, this is our small, cozy, and you know, adequate conference room. So I'd like to welcome again Bob Frosch. I'm not going to give a complete introduction. I think everybody here knows Bob pretty well. He's a visiting scientist in our department, one of our trustees. Has a resume everybody can envy for hours. It's but anyway, Bob also likes to speak about things, and Bob agreed to give us another talk here. So, Bob.
What he means is you had to do this to get me shut up.
That's a possibility.
I actually came to this village for the first time and to talk to people at this institution for the first time in February of 1952 in a driving nor'easter. and I started to work with Brackett Hersey, which went on for 25 or 30 years. So, okay. So let's start with what application-oriented R&D. The distinction I make is only that if you're not doing application R&D, you're probably thinking up the questions yourself. If you're doing application-oriented R&D, somebody else probably thinks up the questions. Or you sit there saying, suppose I was somebody else, what would I like to be able to do? And nonetheless, application or not, this is the great statement about getting anything done. If you don't know how the universe works, you're unlikely to be able to trick it into doing what you want. And just to say what this is all accumulated out is a lot of stuff, starting by being a physicist and doing acoustics in the ocean and a whole bunch of other stuff. Mostly trying to arrange things so other people could do research. Okay, this is the first thing. They all look alike. Everybody says, gee, wasn't GM entirely different than NASA? And the answer is not particularly. The labs were about the same and so on. I would say this institution is probably kind of out at the tail of the distribution from the point of view of the way it's organized. But this is an important thing. They all look alike because, especially if they're big, they're all fractal, and they're made up of, the big ones are made up of a lot of little ones organized in some hierarchical way. I don't know what the fractal dimension is, but I think we can find out. And of course, the organization diagram isn't the real organization. If you looked at the GM organizational diagram, one of the scientists in the research lab, in order to talk to an engineer in a division where they made engines, would have to walk through the CEO's office. But of course, nobody ever paid any attention to that. And real organization, it can be complicated. We had a department at GM Research called operating research, which was mostly social science. It was economics and the epidemiology of automobile accidents, quantitative sociology, marketing, and I got them to hire an ethnologist. And she wandered around for a bit and wondered what to do and found some problems. But one of the problems she found was called parts chasing. You have an assembly plant which has 3,000 people assembling cars. It's nearly a quarter of a mile long, and parts come in, stuff at the front end, components and pieces of metal, and all along the line. And when you get down to the end of the line, there's a gallon of gas in the car and somebody drives it away. So that's an assembly plant, fairly complicated. And different kinds of cars are going down this line, different colors, different radios, different engines, maybe even two brands, very complicated. And sometimes the part that's supposed to go in this car isn't there. And there's actually a trade, a union trade, called parts chasing. Help, we haven't got the part and the person goes around. So there were reports of difficulty with parts chasing. So Liz Bryety went off and insinuated herself into the plant where the things were as a skilled anthropologist and wandered around. And everybody agreed this is the way parts chasing is done. This is the official way. Everybody agreed nobody does parts chasing the official way. But here's how they really do it. And so she wandered around and discovered that here's how they really do it wasn't how they actually did it. There was a third layer of sort of political and social arrangements where they really did it. And the problem was coming because it was sort of submerged that way. And she figured out some things to do about it without disrupting everything. And it was our practice to write a report. So she wrote a kind of an anthropologist's report with a summary of what it all said. And it was also our practice. We had standard distribution list. We'd send such a report to anybody in the company who we thought might be interested. So it went to lots of plants. For a year and a half thereafter, Liz would get a phone call, and there'd be some guy on the end saying, I'm the operations manager in plant number such and such, and I've seen your report, and I want to know how you got into my plant and found all that out without my knowing, to which he said it wasn't your plan. Every single one of them had this 3-layer, 4-layer thing. It's a general phenomenon. Okay, next comment on that.
Thank you, Bob.
And in fact, you know about work to rule strikes. The Paris guys who run the metro can't go on strike, don't want to go on strike, so the word goes out, we're going to obey all the rules tomorrow. R&D organizations don't pay any attention to this. And as I said, this one is kind of out on the edge of the distribution of the relaxed and chaotic as opposed to the organized and systematic. Okay. This is interesting because I saw this in the Globe about a month ago. Okay, so that's about a month ago. And the next slide I got from my opposite number when I was in the Navy Secretariat, who was the UK's science advisor to the Admiralty or whatever, and he had sent me, whoops, that one. And you'll notice the guy with the oars laying down. So if you're not careful, okay, all right. Now then there's the question of, with applied R&D particularly, that it starts with one kind of person, the scientist or the engineer who is designing and building the first one and working out stuff. But eventually in an automobile plant, for example, it's got to go to a different kind of people entirely who are doing the detailed engineering for production, and then to the guys who have to figure out how to put it together and put it together. And they're not the same kinds of people as the guys who designed it. And, you know, this may be a little scientist-engineer chauvinist, but you don't have to worry about the informal part at the front end because the people involved in it have generally grown up in a training where they're self-disciplined with regard to error and how good it has to be and so on. But the guys you hire on a production line, or even for supervision and so on, don't necessarily have the same discipline. So you have to put in a more formal operating discipline, as you do on a ship, for example, And I'm sure the operating discipline on Oceanus and Nor is a lot more stringent on the little boat, where there are 3 guys and they yell at each other and it gets done. So you have to worry about this. Now this is thinking about it in terms of procurement and in terms of satisfying the guy who wants you to do something. And in my experience, the customer for R&D is always wrong. Now that does not mean that the provider is always right. And we'll get to that, you know. The customers, in my experience, don't say what the problem is. They come and tell you what I need is. And usually it's their solution in the head, not their question in the head. So if you go ahead and do exactly what they say, you may be in for a big disappointment on both ends. Because at least now customers here, internal customers, are much more sophisticated and you talk all the time. But if you go between the research labs and the car division, they don't know what the technical possibilities are. They got some idea of how to do it, but that may not be the right way to do it. And they may not be asking the right question. And the technologist doesn't know what that question is. You know, it may be very difficult to invent weapons if you've never actually been in the field trying to use one with a real enemy. And this is an example. The admiral in charge of airplanes says, Mr. Secretary, we've got to have a faster fighter aircraft. Okay, so why do we need a better, faster fighter aircraft? Well, so that we can outfly the other guy in the dogfight. But Tom, the first thing that happens in the dogfight is you make a tight turn, and you're not going anywhere at all. So maybe it's maneuverability. It's like, well, yeah, you're right. And he goes away and he comes back. Well, we need a faster fighter aircraft so we can get to the dogfight while the other guy isn't ready. Oh, but why do you want to do that? Well, we want to shoot him down before he knows what's going on. Well, do you really have to be at the dogfight to do that? So anyway, you go through this, and in the end, the question was, gee, we need a somewhat longer range, faster air-to-air weapon, not, don't go back to the airplanes, go back to this. So you get that kind of a dialogue, and it happens at all levels. This is not so much for here, but this is for procurement people who write specifications and so on as if they were going to buy shoes. That is, they're assuming they're buying something that exists, that if you say it's going to have these properties, it'll have these properties. And in the back of their mind is it's like a shoe store. You know, you look at the proposals and you buy the one that fits. But they don't understand that it's about a future possibility. The result doesn't exist. You can't see it. You can't try it on. You have a problem with discussing what it means. And when you say, I require a missile that will go so far and so on, it's a guess about a possible future. And by the way, the specifications for something don't actually specify. They're, you know, the only thing that specifies the object is the object and how it was actually made. What you write down in the specifications is an incomplete kind of set of things about it. And in fact, you usually don't specify in the specifications how it's to be manufactured. And I've seen cases in which manufacturer A was perfectly happily making an object. Somebody decided there should be 2 sources, so they competed for a second source and told manufacturer B to make the object and gave them all the specs, and manufacturer B could not make the object. There was a little technology and a particular way of doing things that A had that B had never heard of. It wasn't in the specs, just you had to know about that. And if you let a contract to somebody that's going to have to do aluminum welding or high quality steel welding, and they don't normally do aluminum welding or high quality steel welding, you're going to get a mess on your hands, which the Navy did once in a submarine procurement. They let pressure hull stuff to people who didn't have the welding technology. It was a, fortunately, early court disaster. And then, of course, requirements coming from this is my favorite crazy requirement. This helicopter should take off from 14,000 feet on a 90-degree day.
Was that an actual spec?
That was an actual spec. And by the way, it got all through the system, and the cost of this helicopter and the tunnel kept going up until somebody says, you know, in desperation, they come to the research people and say, what's wrong? So, well, look, and that was an actual spec. So, but when you went back into it, it was a kind of an innocent mistake by an ignorant procurement guy who had gotten all the helicopter specs, and he'd gotten a helicopter spec that said this helicopter should take off from 14,000 feet. And there was another spec that said it should operate on a 90-degree day. And he said, well, that looks as if it's two, we'll just make one. We'll simplify it and make one requirement. Okay, guys.
Zero air jam.
Yeah. Then tacit. Now you guys know about tacit knowledge, and but lots of people don't know about tacit knowledge. And here's one of my favorite tacit knowledge cases. Traveling wave tubes are the big radar tubes, big microwave tubes that run the front end of military radar. And they normally have quite a long life, several thousand hours when Hughes was making it, which meant you could put it in the airplane, and when airplanes don't fly all that many hours of that kind, so that was almost the life of the airplane. And occasionally when we'd go out, and the carrier would have a couple in the back bin and be able to fix it. Except one day the traveling wave tubes started having lifetimes like 100 hours, 20 hours, and that's an inventory disaster and all sorts of things. And Hughes couldn't figure out what was wrong. You know, they walked their own production line and everything looked fine. They got so desperate they started looking at the personnel records, and they discovered somebody had retired more or less about the time they were doing this. They went and dug the guy up, but he couldn't think of it. So he started walking the production line, and he came to where they weld the filaments in. He said, no, you have to turn the tube upside down when you weld the filaments in, so they have the right sag when they're welded in, so when you turn it back up, they don't short out. Well, nobody, you know, somebody had learned that on the production line early in the process, and nobody ever wrote it in. Why would you write such a thing into a spec? You don't tell the machinist exactly how to do the machining. You just do it. Okay, this is just a comment that. Figuring out the problem and deciding what it is you're trying to do an application for is usually harder than doing it. And this I just threw into my thing. It's about inventing problems. One of the biggest difficulties in inventing and solving problems is always somebody there says you can't do that. You know. Okay. Now sometimes it's right. I remember standing in the hallway in the Pentagon with Charlie Hertzfeld when he was the director of ARPA and I was the deputy director of ARPA, and some guy we knew came running up and told us about this marvelous new technological thing that was going to solve a whole set of problems. And Charlie listened to this and looked at him and said, give me a number, how big? Within a factor of 2. Within an order of magnitude, in the exponent. Okay, so all that comes out to saying that in many places, application-oriented R&D is thought to be something you do by you write the specifications for the requirements and the specifications, and you have a competition, and you look at the prices and so on, and you pick somebody to do it. You say, here's the money, go away and you'll deliver it in 2 years and we'll test it. And that is a recipe for disaster for all the reasons aforesaid. So it's a contact sport. You have to keep talking to the customer and talking to the supplier and find out whether the supplier thinks they're supplying the same thing you thought you were buying. It's not the shoe you saw, it's the shoe they haven't designed yet. This is R&D, it's not production yet. So, you got to have a very early dialogue, as I've pointed out. You know, what is it we're really trying to do here? And so the current mode of, there's so much conflict of interest if you actually talk to somebody, or God forbid have dinner with them, that you have to do it at arm's length. You can't do it at arm's length. You have to, but since you can't do it at arm's length, you got to pay attention to what everybody's doing. You can't say, oh, well, you know, it's all just fine. You got to.
Can you give this couple of slides over to our sponsored programs office?
I was thinking a few sponsors.
You know, so you know, and you got to keep doing this, because after, you know, in the middle of the development process, you're going to find some stuff that didn't work. It just plain didn't work. So you got to go back and do something else. And if you're not talking about what you really need, the something else the guy is going to do may be the wrong something else, and you get something you didn't want. So what do you do about conflict of bias? You play poker with everybody's hands above the table is what you do. You know, and you trust, but you verify. So you keep watching, and you got to kind of be around all the time. You know, all newspaper reporters and editors have a continuing severe conflict of interest. They are in the business of selling news. So they want news that people will buy. And no reporter who has spent 6 weeks on a feature story will conclude, yeah, it was pretty dull, there's nothing terrible happening. You know, that's wasted time and money. You guys do that with proposals too. After you worked on a proposal for a while, you ain't likely to conclude it ain't worth doing something with. You're likely to figure out what you can put in so it's a proposal. We all do that. That's perfectly reasonable. But, you know, they're just, and it's nowadays an aphorism in the manufacturing business that you cannot inspect quality in. That means if you made it badly to begin with, and the parts don't quite fit, then just inspecting them and throwing away the really bad ones and trying to patch up the not so bad ones produces a cruddy product no matter what you do. So you can't build it and inspect it afterwards. You got to build it right. But you can't audit honesty in either on conflict of interest. You know, you got to audit, and you should audit, but if you find out, as we just found out in the prime mortgage thing, that people were doing some very strange things for several years and nobody paid attention, the audit is gonna compound the mess probably. So somehow or other, you have to get past this business of the thing. Now this is well summed up. The best fertilizer is the footprint of the owner. That's the point about the customer and the provider have got to be working together all the time. Now this was told to me as a Sicilian proverb, but it actually goes back to Pliny the Elder. I just looked it up. He didn't die at Pompeii. He died at Stabia. He was the commander of the Roman fleet. And when Vesuvius went off and they had runners beginning to tell them there was real serious trouble in Pompeii and Herculaneum, he tried to take some ships over there and rescue people, and was overcome by the sulfur gases. Interesting tale. By the way, in addition, there's this account of him, and he the best fertilizer story that he tells is of a farmer not far from Rome who was accused by his neighbors of dishonest practice, because he always had more harvest and better quality than any of his neighbors. His neighbors were all absentee landlords, by the way. And so there was a trial, a formal trial, and Pliny, I think, was one of the lawyers. And the guy came in and dragged into the courtroom all of his farm tools and all of the people. And he says, "We own this farm. This is my family and the people who work for me. These are our tools. We are out there every morning at sunup with the animals in the fields and the so on and so on and so forth." And he was acquitted. So Pliny had it right. Now this is one I don't know what to do about, and it has to do with some slides coming up in a moment. That is, if you're running an industrial lab or even this lab, what kinds of skills do you need? What do you actually have to know in order to do this kind of stuff? And it's not very easy to figure out what it is you can dispense with. And I'll show you why that is. Well, here's a comment on it. Tell you what this means. This was the first time somebody wanted to build a car door out of the outer part, you know, the skin of a car door, out of monolithic fiberglass reinforced polymer. And they knew how to do it, and everything was fine up until they put the whole process together 2 weeks or 3 weeks before production was supposed to start, because they'd never had everything together again. And here's an example of it comes along and bites you later. Everything was fine till they painted the door and looked at it. In order to keep the thing stiff enough so it didn't buckle or crackle, they had molded in a rib down, you know, down the right part of the door. And after they painted the door, every time you looked at it, you could see the rib. Somehow or other, the shape was just enough off so that you can't sell cars where you can just, why, I don't know. It was functionally perfectly fine. But it is a fact that when all of us go and shop for a car, we want it to look like wet vinyl. If it doesn't look like perfect wet vinyl, there's something wrong with the car. So what the hell to do? They got so desperate they came to the research people. And so the polymers guys went over and looked at it, and looked at the manufacturing setup and said, "Can we have a door?" And so they gave them a door and went back to our own pilot thing and figured it out. They knew a lot. In about 2 weeks, they came back and said, "Okay, here's your molding press. I want you to move this cooling line here and run this cooling line 10 degrees higher, and I think we need another little cooling line there. Try it." Of course, they do it. Perfect. No readout. So I happened to run into the head of the division at a meeting, and the head of the division said, "Oh, my guys told me what you guys did. That must have been a really easy problem. They solved it in 2 weeks." I said, no. They solved it in 20 years. It's just that they never got to use the earlier 20 years for that problem. So, you know, if we had gone to the division and said, should we be doing this kind of work on polymer doors, you know, they'd have said, we make doors out of steel. What are you fooling around with polymers for? Here's another one. I mentioned what an assembly plant is like. So you've got 2 or 3 kinds of cars, L6s, L4 engines, and you don't want to put them together because it takes longer to put in a 6 engine than a 4 engine, and you got white ones and blue ones and red ones, and you'd like to paint all the white ones together because you have to purge the paint system between white and blue, and you have all kinds of radios, and so it's a very complicated. And by the way, you'd like all the cars that are going to Toledo to come off about the same time so they can go to the truck and so forth. So you've got a lot of constraints, a big problem. And there was a scheduling problem, a scheduling solution which had really been arrived at by what I'd call cherry picking. That's what the guys called it. What they meant was you schedule for a week. And by the way, this is scheduling for 65 cars an hour, at least 65 cars an hour, 8 hours a day for 6 days a week. And sometimes 2 shifts, so it's 12 days a week. That's a lot of cars. So what they would do was figure out Monday by picking it off a list, and Monday was fine, and Tuesday was harder, and by the time you got to Friday or Saturday, it was really awful. So the guys decided to set up the question of how do you optimize this? And they began to play with it, and they discovered they could write an algorithm, but they could not figure out how to optimize in that algorithm. You know, they could, in principle, you could put it on the Cray and keep trying cases and sort of do that, but there wasn't enough Cray time in the known universe to do that. And there happened to be a lunchroom where all the sort of reasonably senior people sat, and the rule in the lunchroom was you came in and you sat down at the next empty seat, unless you had guests. So to some degree, there was a sort of randomization of who was talking to whom. And these guys were bitching about this problem they couldn't solve. And there was this mathematician, well, it wasn't a mathematician, actually he was a theoretical solid-state physicist. So he listens to this and he says, that has a very familiar ring to it. Now tell me what the question is. He says, very familiar, I think there must be a theorem. He says, I'll go away and think. Then he comes back and he says, well, there is a technique we use in solid-state physics called simulated annealing, which amounts to starting with randomization and then letting it settle in and so on. And the guys looked at it, they tried it, and they had to run it on the Cray. It's a big problem, and it really did the job. And then, of course, once you know you have an algorithm for doing it, you can start simplifying it. You know, if we leave this out, is it all right, and so on. So after a while, they got it down so they could do it on a Sun workstation. And then the problem was, how do you get it into practice? You don't go to a plant manager who's running a $3 billion plant, 65 cars an hour, and say, hey, can we borrow your plant for a week? We got this experiment schedule it. So one of the guys found a plant manager he knew well enough so he could sweet talk him into a more complicated deal. And the deal was that the plant had its own scheduling computer, so they were keeping track of what they were doing. And they allowed us to put our computer, our Sun workstation, next to theirs. And as they ran their week, we'd run the week the way we thought it would go if they did this thing. And he said, well, when things start to get quiet along about July, just before the model change, I'm willing to try it. But every day he'd kind of go by and sneak things. And finally, about the end of May, he said, oh, hell, let's try it next week. And of course, it actually worked. I don't know what it cost us to do the R&D. It can't have been much because it was all theoretical stuff. So, you know, maybe $1 million to do the R&D. It was worth $200 million a year to the company. So, financial guy said so, not me. Here's another interesting. One of the first things my boss at GM, this is a little industrial oriented because I set it up first to give a talk at the American Physical Society in a session on industrial research. That's a little GM oriented. And that may be the stuff that's least familiar to you guys anyway. So. My boss said, what we need is a way to make one-day dies. Now the die is a big steel object, you know, that big, which goes into a giant press, and a chunk of sheet steel comes in and is pressed down and comes out. It's the outer of a door or a hood or whatever. So this is a several tons of die, which is generally made by pouring one sort of about to the right shape, and then it goes to a specialized machining process and gets machined. The right shape, by the way, is not the shape of the hood. because after you take the steel out of the die, it springs back a little. So you fake the shape so it springs back. I said, we need a one-day die. It takes too long to make all these dies. Now, that wasn't the problem. It was really a procurement problem. The procurement problem being all the manufacturers have the same seasonality, so they all suddenly are yelling to have their dies machined at the same time, and there's a lot of jockeying for a limited capacity. So if we could pour a die in one day, that'd be great. Now, to shape and size and so on. Now, it was well known there were tryout dies where you only punch five of them to see if you got the shapes about right. And they were made out of a zinc alloy, but the zinc alloy wore out, so you couldn't do that. But the guys thought they had some ideas about it, and so very good metallurgy department, they did real examination of the aluminum, copper, zinc, ternary alloy phase diagram. They did more or less the whole diagram, and they found something they thought would work. And they actually made a die about that big and persuaded the guys who punched the air cleaner covers, the air filter covers, to try it out, and they punched a million out. So, but we could never sell it to any of the big die guys. They wouldn't take the risk. They didn't try that. There were some of the union guys who told me there was some backdoor footsie with the machining companies. I don't know. But anyway, so, it was the wrong problem, and so we just forgot about it. And one day somebody came in and said, we have this little interlock that has to be put in for safety purposes, and it has to have the creep and strength properties of steel, but it can't be cast, and we're machining it, and it costs, like $20 for each one, and it's absurd. Can you guys do something? I said, I'm not sure. So they went back to the aluminum, copper, zinc, and they went back to the phase diagram and said, there's a place that looks like it. They found a way to get into the right place in the phase diagram, and they had an aluminum, copper, zinc alloy that had 1/1000th the creep of other aluminum, copper, zinc stuff, and the strength of steel roughly, and wow. Furthermore, it was die castable, so it cost about 3 cents each or something. So that was so all that stuff with the aluminum, copper, zinc, that was irrelevant, except when it became relevant. The motto I had, somebody would say, why do you have a big metallurgy department? The answer was, well, we make a lot of stuff out of metal. It could be I'll come back, which was not generally in industry considered a good answer. But no, I've been told, in fact, at the Physical Society, one of my colleagues who talked about his industry, that's not a good answer. You'd be spending lots of money on stuff that didn't matter. I'm not sure. Anyway, knowledge matrices. This is just a way of thinking about these things. That is, suppose I want to make a more efficient or a lower emissions auto engine. What do I have to know about it? Even if I'm going to do it by improving the shape of the combustion chamber, I got to know about the combustion chemistry. I got to know about how to set the flame off. So I got to know about something that will work with this situation. I got to get the stuff into the engine and the exhaust out of the engine. I got to wonder whether it's the same heat or different heat, and where does it go. And the piston has to go up and down, and the materials have to be right, and so on and so on and so on. And after you've done that, you've got to go to the next level of detail. So you get something that looks like this. Down the left side are all those factors, and down along the top are all those disciplines. So, as you guys know, it's a complicated stuff. You make stuff out of electronics and electricals and materials and pressure and fluids. Again, this is well understood here. It is not necessarily well understood in boardroom. Okay, so, and my conclusion was that if you're going to do this, you got to have some kind of an organization. And it's got to be fairly central. And I'll come to more. At least it's a matrix managed thing because you're managing a matrix of knowledge. Now, for example, the total of the organization, GM needs mathematicians, but how many mathematicians does the Pontiac manufacturing division need? Well, maybe one, maybe none, but you can't operate that way, and the division may not even know it's a mathematical problem they have. So somewhere there has to be some central oversight that says, hey, we do. And this institution has that. It sits around and says, you know, what kind of departments do we need? Well, we need physical, oceanography, and so on. This department does that. I mean, I've heard you guys do it. I mean, what kind of skill do we now need that we didn't need last year that we better have somebody around here? Okay. And by the way, at least in industry, and to some degree here, you do other stuff. You know, we used to develop cars. We worked on how you manufacture cars. We had the guys coming in with the door rib, and like the Navy comes in here and says, we had this funny, what do we do about? It keeps an eye on what the rest of the world is doing in S&T. It has a memory, you know. I actually had to tell somebody, yeah, we used to have a guy who knew about Greece, but he retired. but I can probably find you somebody in the university. Okay, and you do education and training. Now, if you read the literature on industrial R&D labs, it tells you it's all about product development. Either they're lying or they don't understand. But it's not. Okay, now, two management systems I learned. One is well known. That's David Packard, the Packard of Hewlett-Packard, and he's written a book and he's talked about it. He called it Management by Walking Around. That is, how do you know what's actually going around? Story. Sonobuoys. Everybody here knows what a sonobuoy is. And at one point in the history, there were 3 companies making sonobuoys, 2 aerospace biggies, and a third company that nobody quite understood how they got the contract because they were in the business of making cheap radios. And sonobuoys were then made in, I think, 5,000 or 10,000 item lots, of which they would take a sampling, like 100, and take them out and fly them and drop them to qualify the rest of the lot. Very good practice. Everything's going along fine, and suddenly one day, aerospace biggies sonobuoys are not qualified. And whoops, aerospace biggie number 2 sonobuoys are not qualifying. And the radio manufacturer's chugging on, sonobuoys are qualifying. So it got pretty bad for a while. The Navy wasn't getting any sonobuoys. So they came around and said, they always come to R&D when there's something, go off and look. And so I had a guy named, on my staff, named Peter Waterman. Some of you might know. He was a radar engineer from NRL originally. And the other thing this audience will understand, he was a Vermont man. Very skeptical, tough guy. So Peter went off on a 2-week trip to see what was going on. He came back and said, well, boss, it's like this. Aerospace biggie number 1, I come into the place and they immediately show me into the Management Information Center. And they show me all the records and how they keep track of everything and so on. But after a while I began to look at everything looked like it was kind of stale. It was sort of 2 weeks old and I couldn't get in. So, you know, after a while I left and I went to aerospace biggie number 2. Same deal with the Management Information Center. So then I went to the radio company and I went into a kind of a dinky little office with an old ripped chair and the 2 guys sitting there. We're talking away about the business. Finally I said, where's your Management Information Center? And they said, what's a Management Information Center? And Peter says, well, you know, you're supposed to have this, and he describes it, and finally the guy says, oh, my brother and me, we don't have any time for that. We got to spend all our time walking up and down the production line making sure it's being done right. Okay, then the other is, this one is my own recent formulation. It's called Management by Asking Questions. So what questions? The first, most important question you got to ask, so what's going to go wrong? Nobody wants to tell you what's going to go wrong. Then there are others, who wants it, why, well, and lots of things are left out. So if this thing breaks, how are you going to get inside it and fix it? How's the guy who's going to have to get inside it and fix it, who doesn't have your funny tool that you've made up for the purpose? That's, so what can I, in the course of my life, I have been responsible for a couple of ships that had to carry very heavy objects. The Artemis transducer that was 50 to 100 tons, where we took a 10,000-ton tanker and cut a sea chest through it. Okay. So in one of these cases, I'm hearing all the designs and so on and so on. Just to the hell of it, I said, so what happens if the spring breaks? Don't worry about the spring breaking. It has a factor of safety. After a while, you know, humor me. Go away. Tell me what happens with the spring. So the next day I get called to the project office and everybody's kind of gray and green. They said, well, boss, if the spring breaks, and we assumed it was sort of in the middle, there's a wave that comes, this is fairly deep, a wave comes up the line. And when it gets to the thing that holds it, the thing that holds it jumps up and comes down and breaks the ship. And it goes to the bottom. However, now that we looked at it, it's very easy to fix. We put a little damper in here and a wave damper. Always ask what can go wrong. That's the, well, I have other anecdotes. One of the issues, which is something of an issue here, with respect usually to the Navy or some other customer, is, okay, so now I solved the problem, I have the piece of equipment. How do I hand it over? What do I do? And the usual solution is, well, you've got this patent and you've got all the paperwork, and you put it in an envelope and you send it to them. That is useless. In the end, either somebody who actually understands has to go, if for no other reason than the tacit knowledge, but actually to make it clear what you actually did. We all have the experience with the computer stuff and the telephone stuff, where it does it says push this button and you look, what button? You know, oh, that's the one around. Yeah. So you have at least that. So you have to send somebody, or you have to bring somebody in and give them a course, and you have to keep being available. So we had this problem in the GM labs, and somebody noticed that the best people for this were the guys who'd left the labs and gone to the division. And we didn't have that happening very much, so we invented a way to have it happen more. We hired people for the labs who didn't want really to have a research career. They really wanted an operating division career, but they had the right kind of background. In the end, we sort of settled down on about a master's level, engineering usually. And they came into the lab, and if we had something going with the division, you know, next year we're going to finish this and we're going to send it over there. They worked on that project for anywhere from 6 months to a year and a half, and at the end of it they got a promotion and they were sent out to that division, and they're the guy carrying the new technology. And that really worked. It was very hard to get people from the divisions into the research lab. Mostly they didn't have the same kind of education, and they didn't have they weren't all that interested. You had to find people who kind of bridged the gap. Oh, then I'm running over time. Okay. This will take a second or two. No, I mentioned the matrices, but here's an example. I tried to explain this to you once, and here's an example of what I try to think about. So all of this simultaneously. You got this engine block, and you're working on the engine block, but it's got to fit into an engine, so it can't stick out. I mean, you got this long thing that can't. And it's got to match to a powertrain, and it's got to go in the vehicle with fuel and all that, and the vehicle's got to drive and so on. Eventually you're up there. But also it's made out of something, iron and carbon that came from someplace. And it came from someplace, originally ore, iron, gas. It helps to know all this. And what's going to happen to it when you throw it away? Well, that's of some importance. And in fact, that loop actually goes all the way around from scrap. GM, when I was there, was running the world's largest ferrous foundry company, like twice the size of U.S. Steel, anything like that, because it made all the engines and the transmissions and so on. It bought no steel or iron. It ran entirely on the clippings from the sheet steel that was bought to make the vehicles. Both what's called engineered scrap, namely you can only use so much of a sheet of steel no matter how clever you are. So you got all that left over, and then there's scrap and old engines and so on. Bought no iron. It was fascinating.
But how was the alloy corrector that adjusts that?
Oh, you threw in other stuff, you know, and you burned out some of it, so on, and you could do that. It went through a cupola with the right chemistry. By the way, that's an interesting side story. A cupola is about 10 stories high, sometimes 8 stories high, and in the top of it you put either ore or iron or steel or whatever, and you add the coke and you add lime and this and that, silica sand, and you've got gas burners, and it all melts down, and at the bottom out comes cast iron. It turned out nobody actually understood the thermodynamics, thermal performance, and chemistry of this thing. It was one of these trade things. You built the new one with some improvements over the last one. And my conclusion was that a Sumerian bronze smith of about 3000 BC would come into the plant, be appalled by the size, not quite understand the fuel, but realize what was going on. That when the guy went over and looked in, he knew exactly what he was looking for. But nobody, so the guys had spent about 2 years. They borrowed one that was down, and they measured the temperatures for the first time, and it was the same kind of thing. You ought to move the gas jets down a little bit and put a little more of this, and it was very interesting. So knowledge is very fascinating. Now I could go on through this, but maybe I ought to stop.
Let him go. Go on for a few more.
Please don't.
Continue.
Okay. How do you find out whether I wanted to know whether the GM Research paid the rent? You know, we were funded centrally. And in principle, the divisions thought they were taxed in order to run us. Nobody knew where the number came from. It went up and down every year, not having anything to do with our success or failure. But if business was good and we had the right boss, we got some more money, so it was really good. And you know, I concluded you can't measure you can't say how many projects succeed. I mean, they're all different sizes and shapes. What does that mean anyway? And you don't even know what the success rate ought to be. You know, how good should the projects be? And since you have things like the zinc alloy, which was a failed project and a successful project. I don't know what all of that means. And then I had a NASA center director once. We had a meeting of all the directors. He came in and he said, everything my lab did last year was successful. And I said, so you're going to try something else? Which was unfair because he ran a very good lab. He just had a funny idea of what we wanted to do. Okay. Now, so my thing was that the organization should pay the rent. That is, the GM Research Labs should be paying its rent. Now, what did we do? Well, what we did was I went to every department and said, give me a list of the projects last year that you transferred to a division. You know, just slice off a year, don't worry too much about end effects. And give me a list of the things, and give me your estimate, which I won't believe, but your estimate of the value of it to the division. What we used that for was because we got 150 things on the list, and we used their estimate to rank order which ones we were going to take seriously. So we ended up with about 16 allegedly big ones. And then I got the financial officer for the labs to go to the financial officer in the division and say, hey, our guys say you got this and it was worth such and such. What do you think it's really worth? So out of the 16, we had 12 that looked like they were real. And they had two properties. One, well, three properties really. One was they were worth a lot of money. The guys in the division thought they were worth a lot of money. They had staying power. That is, they were going to go on being a savings. It wasn't just a, well, we saved a little this year, but it won't matter. They were something that was going to go on saving money. And mostly they were production or manufacturing. We couldn't follow an improvement to a car to find out what it was worth. Suppose you improve the combustion chamber of an engine. Well, by the time they make the engine, there's an improved combustion chamber, and they fiddled with the starting, and they fiddled with this and fiddled with that, and you can't figure out what it's worth in the car. But you go on a production line, they take 5 people off the line. You know what it means. So in the sampled year, we had 12 projects out of 120 or whatever. And we ran them for a 6-year project life, which was the GM standard. Even if it went for infinity, you did your value estimates on 6 years, and we computed an internal rate of return. Everybody know an internal rate of return? Anyway, you take the future cash flow, you discount it back to the present by whatever you think the discount rate is, and that gives you a value for the 6 years, and you divide it by 6, so it's an annual value. And then in the denominator of the sum of the 12 projects, we put the entire cost of the lab for a year. So it's a lower bound. There was other stuff. And that gave us an internal rate of return of 70%. Now, what an internal rate of return means to financial people is that's about the percentage rate, that's equivalent to the percentage rate you would get in a bank if the bank were giving you 70%. So, you know, did we pay the rent? Oh yes, we paid any other investments like that. So instantly we went to the financial people and said, hey, next time you're worrying about, look at this. And we got 2 answers. One, the research labs doesn't make a profit, it's a cost center. It says so right here. And 2, that's sort of 180 million. We can't find that in the bottom line. It was a $126 billion company. Mind you, the books were kept 12 significant figures. All I should never mind. Okay, now this side. I mean, and this is kind of a valedictory comment. The Navy's research community can be as marvelous as possible. It doesn't mean the Navy's going to win any wars. There are too many ways to screw things up beyond. That's enough. Questions,
we have time for a few questions here.
Vicious attack.
No vicious.
I actually have a comment, just an observation. The Navy now is implementing, for instance, in these reach-back cells that the Navy develops, where they do run oceanographic and acoustic models and then send information out to the fleets. They do that sort of synthetic alumni thing. There are people from the who have been at the reach-back cell who are on the operations officer's staffs, the commanding officer's staff in the fleet. Yeah. And those are the people who
well, the military services have always been fairly good at that, in the sense that they're all besotted with education, and they tend to keep track of people's experience, and they like to do that. It was an interesting. I did some studies in the State Department where they don't do that. State Department won't take anything and put it into the planning for where you want to go. In fact, to the extent that when Kissinger was Secretary of State, he made a rule that says regional and area experts are not to be assigned more than once to their region they go native. To which the answer is, isn't that nice? Now I know where to get a friendly native I can go.
John? I was interested in your experiences Associate Director for Applied Research at WHOI, since we don't have anybody with that exact title now. If you could expand on what that was.
Okay, this was, remember when this was. This was 1955 to 77. And Paul Fye and I cooked up the title and the job because we thought it would sort of move things into more application-oriented stuff. And roughly speaking, most of the institution didn't want to have anything to do with it. And there were some people who were working with the oil industry. There was the same crowd who'd been working with the Navy all along and didn't need any particular encouragement or discouragement. But as for other people thinking about, gee, where is there out in the world of industry and government organizations that this stuff might be useful for, nobody wanted to think about it at that point. I logged it as a failure, more or less. There were a few things that happened, but I was here for what, 2 years.
Interdisciplinary work was one of the contributions.
I think we managed some interdisciplinary stuff. Charlie Hollister got the bug to study a bunch of things in ocean bottoms and continental slopes, and that's where the stuff about I don't know what to call them. He called them storms. That was a little violent, but you know. Actually, I guess some of it was gyres, the small vortices coming close to the slope and making trouble. That came out of that. And he did a lot of work on, he got interested in deep ocean disposal of nuclear waste, which is probably still a very good idea, but nobody wanted to take it very seriously. I think he might have made something out of it, but he got off into other activities and then he died prematurely. So nothing much happened to him. It was not one of my great successes or our great successes. A lot of people just plain, you know, we don't do that. We do pure research. I didn't make the sale, John. Okay. Other comments?
Okay, let's thank Bob again.
I had a question about what you're